Hello people, now we are going to see some solved problems for the Taylor series. So basically, how do we build new Taylor series, how do we integrate them, differentiate, compute definite integrals, just to see some practice problems. So I will walk you through the process and give you hints. So you will need to work some details on your own. There are plenty of details on the slides, but it is very important for you to actually do the work on your own. So one of the reminders is that our power series for a function f, they are unique, and actually those are our Taylor series. Now we learned that once we are given a function f, we can generate a Taylor series, and usually we are given also the center of the series. Often it is 0, so those types of series that have center at 0 are called Maclaurin series. But often we have center that is a number different from 0 depending on our needs. So sometimes it could be 2, sometimes it could be 1, or pi over 2, pi over 6, depending on the situation. So a Taylor series can be generated by an infinitely differentiable function. So that's easy process. It takes some time to compute enough derivatives to see a pattern, as we will see in some examples, and then you generate the Taylor series. After that, we will use ratio test most of the time to prove that series converges. And then we saw previously that there is a theorem that helps us prove that actually the series is converging to the function that was used to generate the Taylor series. So those are the pieces that need to be put together. Now, to generate new series, we know that we can differentiate the existing series, integrate them, all of that term by term, because the Taylor series are power series, and we know that for the power series we can differentiate term by term and integrate term by term. And the radius of convergence remains the same for the new series. Also, we saw the tricks. One of them is replacing x in an existing series by some expression containing some power of x. So basically we are generating a new series simply by replacing an x by a power of x. Also, we can multiply or divide the series by some power of x that produces a new series. We will see some examples, and we will see also some examples how to actually compute limits using the power series, on top of seeing how to use power series to compute some integrals, indefinite and definite integrals, for functions that previously we were not able to compute. And we can also add, subtract, multiply, and divide existing power series to get new series. Now, we will not do these two operations because they are a little bit heavy in algebra and computation. It takes us some time. There are a couple of examples on the slides, but we are not going to focus on them. It's just for you to see that that's actually possible. So first way of creating new series from an existing one is actually to replace x by an expression. So if I need to generate series exponential 2x, well, I take just the series exponential x, in this case exponential t, and I will replace t by 2x simply in the series. So that's what's happening here. We are simply replacing t by 2x everywhere, and we create a new series. So there was no effort involved here. Obviously, we could use exponential 2x and do all the computations for the derivatives. We need to generate a certain number of derivatives, maybe 4, 5, 6, to see the pattern, and then use the formula for the Taylor series to create the expression that we see here. So that would be a long way. Since we already know the expression for exponential x, for the series of exponential x, we are just replacing x by a new expression 2x and getting very straightforward result. We will do the similar procedure for exponential of x squared. So basically each t is replaced by x squared. That's simple, and then we get a new series. So now this series can be differentiated, integrated, we can do things with it. And then if we need to produce a series for exponential negative 2x, instead of doing all the work, we can just plug negative 2x instead of t and replace it, and we get a new series. So that's like the lazy way to get new series. Another way that we saw already previously for our power series, which is true also for the Taylor series, is if I need to multiply sine with x squared and I need to get the series. So obviously I can proceed with the derivatives. Now you will have product rule to apply several times, so that's very tedious and long. A smarter strategy is to use a series for sine that we already know and we memorized, because we need to memorize a certain number of series for sine, cosine, exponential, log, tan inverse. So those series are used often, so we need to kind of memorize them. So I have a series for sine x, and now all I do is multiply that series by x squared. So I'm multiplying the series by x squared. So as a result, the power on x will increase by 2. So I have 2n plus 1 plus 2, so it's going to be 2n plus 3. So I have a new series for the function x squared sine, and I obtain it with very little effort. And we know already that the radius of convergence remains the same. So those are some of the results that we already saw with power series that are true for the Taylor series, obviously. Similarly, if I have ln of 1 plus 3x squared, for instance, we already computed a series for ln 1 plus x. We did this process the hard way, so computing the derivatives. We could also integrate the function 1 over 1 plus x to get this result. So there are two ways, and in this case the series is convergent for x is in absolute value smaller than 1. So that's very important here. Now I need a series for ln of 1 plus 3x squared. So I will replace x by 3x squared everywhere. So I'm replacing x by 3x squared. X that is here becomes 3x squared, and obviously x that is here becomes 3x squared. Need to be consistent. I need to replace it everywhere. So I have a new series, and I have the radius of convergence. If I do the work, I'll get the radius of convergence of 1 over radical 3. So it's very important to replace x everywhere. Okay. A similar example with log minus 4x cubed. So we again use ln 1 plus x, the series that we already have from the beginning, and we replace x by negative 4x cubed. And again we replace it everywhere, including in the limitation part where we have the interval of convergence. So that's very important. I mean, we cannot forget that part. So here we get a new series, Taylor series, and the radius of convergence is 1 over third root of 4. Now a tricky one is given here. We are given a series but not in sigma notation. So basically we have some expression and we need to figure out what is the sigma notation. So that's a little bit more challenging. So we need to see the pattern here. So we see 1 time, and here 2, and then 3, and then 4. So we see that downstairs we will have n at some point. And then we have 2 to power 1, 2 to power 2, 2 to power 3, 2 to power 4. So again we have 2 to power n downstairs. And this is an alternating series. It starts with plus 1, then negative 1, plus 1, minus 1. So we need to take care of the sign. So here normally you would write n minus 1. If you write n plus 1, it's fine, it doesn't change anything. So make sure that you pick up the sign correctly, and now we have the expression. And the idea is to recognize this shape from the table that we saw at the beginning of the slides, where we have a couple of series that we need to remember. Obviously this is a little bit trickier because we need to rewrite things and then check the table to see what function looks like, the series of which function looks like this. So basically we are trying to reverse engineer things. And then consulting the table, we realize that this is a series xn over n alternating series. So now this is ln 1 plus x. In this case, x is 1 over 2. So this was a little bit trickier because it goes in the other direction. Normally we are trying to find the series, not to recognize the series. So this is like a little bit backwards. So it's good to see this type of problems. They can be interesting to solve. Obviously you will need to consult the table of the Taylor series because we have a couple of those that are regular and we need to remember them. So table is very useful for revision. Now, one of the important uses of Taylor series is to compute the integrals. So we remember that exponential negative x squared, this function doesn't have an antiderivative that we know about. So basically we cannot just find the antiderivative for this function, and it is difficult to integrate this then. Now, since we know the Taylor series for exponential x, now we are going to proceed to the computation of the integral using the Taylor series. So the process is simple, but it has several steps. So the first one is we have exponential x, which is one of our classical series that we need to remember. So we have the shape here. Now we need to replace x by negative x squared, obviously. Fine, we replace that. So now we have a series for exponential negative x squared, and the radius of convergence is the same. So this is valid for all x, so it remains the same. Now what we need to do is to integrate this series. We remember this is alternating power series, so we can integrate term by term. So that's very important to remember. So integral of the function will be equal to the integral of the series, and now the result about power series tells us that we can actually integrate term by term. So we integrate only the part with x, obviously. N is a number and this is a sign, so it's a number plus or minus 1. So we take them outside of the integral. So we integrate exponential x to power 2n. We integrate it normally as if nothing happened. So when we integrate normally, we have the constant of integration and we need to write it. We should not forget that constant. So that's why we write it at the beginning so we don't forget it. And now, so the integral of x to n is x to n plus 1 divided by 2n plus 1, and then we regroup everything so we get our series for the integral. So even though we don't know what's the function, what's the antiderivative for exponential negative x squared, we still have the series expression for the integral. So this is amazing and it's very useful. Obviously we observe that this is an alternating series. It is very important to remember that for the alternating series, the remainder or the estimate of the error is the next neglected term. So in case we are approximating values of this integral, depending on our expansion on the Taylor polynomial, the error will be smaller than the next neglected term. So that's an important thing to remember, and that's a property of alternating series. So if we need to evaluate the integral between 0 and 1 of this function, we are going to simply evaluate the integral of the power series. So the constant will not change anything when we integrate, when we evaluate in two bounds. So constant will disappear anyways. And we observe here that at x equals 0, all of these terms will be 0. So that's why they disappear completely from the final result. And we have x at 1, so we'll put 1 everywhere, minus the series when x is 0, which is 0, so that's why it doesn't appear here. So we have, as a result, an alternating series, and the numerator is 1 all the time. So basically this is our series with x equal 1, essentially. So depending on the precision that we require, we will add more or less of these terms. So more terms we add, better precision, obviously. In this particular case, we are asked that the error be smaller than 0.01. And now we are using the fact that this is an alternating series and the error is smaller than the next neglected term. So as of now, I don't know how many terms I need to add actually. Where do I need to stop? Do I add only the first 3, the first 4, 5, 6? How many terms do I need to add in order for my result to be correct to 0.001? So how do I decide? Well, I decide based on the estimate of the error. And we said this is an alternating series. The estimate of the error is the next neglected term. So I will try to evaluate the last 2 terms here just to see what is the value. Maybe one of them is smaller than 0.01. So that will be my estimate for the error. So I will stop at the previous one. So let's see what do we have as estimates. So it's very important to remember that we have alternating series. That will help us find the estimate for the error, and we know the estimate of the error is the absolute value of the next neglected term. So let's try to see 2 terms in the series. What are the values? So we chose this term here and this term because they are far enough. So let's see if we are lucky with them. So computing the first one, we get the value approximately 0.046. So that's not smaller than 0.01. Okay, so this guy is bigger than the required error, so we need to test the next one. So testing the next one, we get a value that is obviously smaller than 0.001. So this term will be our error. Okay, so this will be estimate for our error. So if I go back to my series, this term will be estimate for the error, and all the other terms will be used to approximate the value of the integral, because the error needs to be smaller than 0.01 and this term is smaller than 0.01. Therefore, that's good for me as an error. We remember this is alternating series. If I stop here, the error is smaller than the next term, and the next term happens to be this, so which is smaller than what they required from us. So that's the logic. So I will add the first 5 terms and I get an approximation. And this approximation is correct within 0.001. So that's fine. So that's one type of questions. Find an approximation for the integral using the power series, and that approximation needs to be precise to a certain degree. Now, another type of question would be, okay, I would like to know how many terms I need to add in order for the approximation to be correct to certain number of decimals. Let's say here 5 decimal places, which means that the error estimate needs to be smaller than 10 to the power minus 5. Now we remember that our series, I'll go back, our series is here with 1, you see, it's 1, 1, 1, 1, 1. So I have an alternating series with x equal 1 here, and then the downstairs is 2n plus 1 n factorial. So that's what we see here. So this thing needs to be smaller than 10 to the power minus 5. Okay, how do I figure out what's the value of n? Well, unfortunately in this case you will need to use trial and error. There's no much choice here. So you start picking some values of n and testing. Obviously if you take 10 n equal 11,000, it's probably going to work, but you will need to add 11,000 terms in your Taylor polynomial. You don't want to do that. So you need to find n that is just good enough. So you don't want to overkill the process, because you will need to add many terms in the Taylor polynomial to get the approximation. You don't want to do that. You want to do the minimal effort but sufficient to satisfy the requirements of the precision. So here they requested 10 to power minus 5, fine. I will need to try couple of values of n. So if I try with 6, it doesn't work, it's not smaller than 10 to power minus 5, 7, and in this case 8. When I plug 8, I get this expression here, and this expression is smaller than 10 to power minus 5. It's actually 1.5 10 to power minus 6. And 7 doesn't satisfy this criteria, so basically I need to go to an 8. Okay, so that means that I will need to use polynomial, Taylor polynomial of degree 7, I think, in this case. So basically in this process here, I will need to go up to, you see here, 4 factorial, 5 factorial, 6, 7, and so the 8 factorial is satisfying the error, so I will need to go up to 7 factorial downstairs. Okay, so that's the idea. So those are two types of questions. Either how many terms do I need to get certain precision, or you compute an approximation to certain precision that is already given. Another use for Taylor series, on top of the computation of integrals for some difficult functions to integrate, is to find limits. So computation of limits. Obviously this needs to be set up in a way that it works, because otherwise it defeats the purpose. So in this particular example, we have indefinite form 0 over 0. So obviously you could use L'Hopital a couple of times and get the result. But this is just illustrating how to use Taylor series in cases. This one is, let's say, straightforward for L'Hopital, but some cases could be more complicated. So how do we do the work using the Taylor series? So we have exponential x, we have the Taylor series, and then we need to subtract 1 and x from the Taylor series. So we write the Taylor series for exponential, minus 1 minus x. So these two first terms disappear. So this is the result. And then we need to divide it by x squared. Obviously, this is set up in a way that everything works nicely, that the numbers work beautifully. So we divide by x squared. So you see this will become 1, then this is x squared. So basically things simplify a little bit. And now we take the limit when x goes to 0. So we take the limit here when x goes to 0. So basically we have 1 over 2 plus all the other terms are 0. So in this case it was kind of easy to find the limit. And when I say again, obviously everything is set up in a way that things work nicely, because these are practice problems, so we want them to work nicely. We can also multiply Taylor series, so we are not going to do it because it takes some time. I'm just showing some examples, and you see here they ask only for first 3 non-zero terms in the Maclaurin series, because obviously each series has infinitely many terms, so there's no way for you to multiply this forever. The idea is just to get a sense of the shape of the product of the two series. Obviously you can expand exponential x sine x, so you compute a lot of derivatives, so you'll have product rule very often, so that will be a little bit long. So that's why maybe the effort of multiplying these two series is worth your time. Again, we are not going to use this. Really, this is just an illustration how to do it. So basically you pretend that these are polynomials, so it's not like infinite series. We pretend that they are polynomials, and then we multiply the terms and then we add them. So it's a little bit long and tedious in order to get an idea of the shape of the resulting series. Okay, so again, we are not going to do this actually because it takes some time, but this is just an example to show you that actually what you do is you treat the series as if they were polynomials, and then you multiply them term by term essentially, and then you add pieces. So it's a little bit long. And that's why they ask only for a couple of terms at the beginning, because otherwise we will spend our life doing it. We can also divide Taylor series. This is just another illustration. So if I need Taylor series for tan x, well, I can just divide sin x over cos x. So I divide the series. How do we do that? Well, we do the long division. So we pretend that these are like polynomials. So we do the classical long division. Obviously, you cannot do it forever. That's why they ask only for a couple of terms to see the beginning of the series. And again, we are not going to do this because it requires a lot of work. This is just an illustration. So if you need to divide two series, you actually use something similar to long division. Now, some practice problems, and I will walk you through them quite rapidly so you can do some work on your own. It's important just to see certain tricks. So, first question is find the Maclaurin series. We remember Maclaurin series is special Taylor series that is centered at 0. So find the Maclaurin series for a function f. They don't give f. And find the radius of convergence. But they give us the form of the derivative. So derivative at 0 is given by n plus 1 factorial. So that's useful for our Taylor series, or here Maclaurin series, because we know the shape of the Taylor series. We have derivatives at 0, xn over n factorial. So basically we are replacing the derivatives by n plus 1 factorial in this expression, and then simplifying things. So n plus 1 factorial is equal to n plus 1 times n factorial. So n factorial up and down will simplify. So we have this expression for our Taylor series. So the mysterious function, whose derivatives are given as n plus 1 factorial, has this Taylor series. Now, so that was like straightforward, just plug in. The general term is obviously n plus 1 times x to power n. And they ask us to find the radius of convergence. So how do we do that? What do we do to find radius of convergence or interval of convergence? Well, in general, what you will do is use a ratio test. So here again, we use the ratio test as usual. So we have an plus 1 over an. And we remember that an is n plus 1 xn. So in this case, an plus 1 is n plus 2 xn plus 1 divided by n plus 1 xn. So we simplify a little bit and we get this expression. So x doesn't depend on n, so it can go outside of the limit. Obviously the absolute values need to be preserved, so we have absolute value x times limit of this expression. Obviously this is 1, so we have absolute value of x as the limit of the ratio. And we remember from the ratio test that in order to have convergence, the limit that we compute needs to be smaller than 1. So this means that absolute value of x needs to be smaller than 1, so x needs to be in interval negative 1, 1. So radius of convergence is 1, we get it from here immediately. So our series that we had here is absolutely convergent, okay, for values of x that are between negative 1 and 1. Quite straightforward. This is similar example where we need to find Taylor series for a function f and we don't know what's the function, and the Taylor series need to be centered at 4. That's important information. We need to find the radius of convergence and we are given the shape of the derivatives. Okay, at 4. Fine. So we use the formula for the Taylor series centered at 4. So that's why we have x minus 4. And all of our derivatives are evaluated at 4. Okay, because the series is centered at 4. So we use the formula, plug in the expression for the derivatives, simplify a little bit, and we get the general term for the series. Again, this is an alternating series. And we need to now find the radius of convergence. What do we do? Well, ratio test again. So we have the expression for the general term and we compute the ratio test. We see here that we have x minus n over 3 and then n plus 1 over n plus 2. So this part here with x is going outside of the limit because it doesn't depend on n, and we need to preserve the absolute values, and then the limit of the expression with n is 1. So basically we remember that the ratio test tells us that the series is absolutely convergent when the limit of an plus 1 over an is smaller than 1. So we just rewrite it a little bit and we get the interval of convergence, and the radius is 3. So radius is half of the interval of convergence. You can get it from here also. 3 goes out, so you have x minus 4 smaller than 3, so that's the radius. 3 is radius, and this is the series that is centered at 4, right? Here, the series was centered at 4. Okay, so those are like straightforward examples. Here, they want first four non-zero terms of the Taylor series of a given function centered at 2. So the center is 2, so we will need to evaluate all the derivatives at 2. It's very important. And they need only first 4 non-zero terms. So we don't need to produce a lot of derivatives. So in this case, f is given, so we compute derivatives systematically. So we need only 3 of them because we need 4 non-zero terms in total. And then we evaluate all the derivatives at 2. Luckily, all of them are non-zero, so that simplifies our work. So the Taylor series, as per the formula, centered at 2. So all the derivatives evaluated at 2. So now we only need 4 terms. So we have the first term, the second, up to the 4th term. So this ends up being a polynomial degree 3. So this one was also straightforward computation. We already know the expression for ln 1 plus x, and if we want to recompute the Maclaurin series, it's important to get the shape of the derivatives. It's important to spot the pattern, and every time you can keep the factorials in the expression, keep them because they are important. They simplify your life later on. So instead of writing here, let's say 6, you keep 3 factorial. It's much more useful. Since we are dealing with Maclaurin series, we need to evaluate all the derivatives at 0. So we get the values here. And now we plug everything into the Maclaurin series formula. So we realize that the derivatives look like this. Evaluated at 0, we get this expression. So we will use this expression into the Maclaurin series. So now things simplify a little bit, and we get the general expression that we already saw in a table for the log 1 plus x. So this is Maclaurin series. It is centered at 0. You see the general term is x minus 0, obviously. Fine. So to see the interval of convergence or radius of convergence, we need to use the ratio test as usual. So we have the general expression here, xn over n, and this is just for the sign. Since we have absolute values, we drop the sign anyways. And in this case, we have that x needs to be smaller than 1. So the radius of convergence is 1 for this expansion. So this means that this series, the series here, is equal to our function for x's in interval -1 and 1. Now a funny situation. Here we need to find Maclaurin series for a polynomial. So this is polynomial degree 4. And then we need to find the radius of convergence. So this is a little bit funny because we have a polynomial as a function. So let's start. They need Maclaurin series. That means we need to center the series at 0. So we need to evaluate the function and all the derivatives at 0. So let's compute the derivatives for the polynomial degree 4 that is given here. So basically we just compute derivatives simply and we evaluate them at x equals 0. So all of these expressions here, they have x involved. This one is a constant 48, so it's always 48 for all values of x. So at x equals 0 it's also 48 obviously. And this is a polynomial degree 4, so the fifth derivative, so the derivative of 48 is 0, and then all the other derivatives are also 0 obviously. So this means that our Maclaurin series is actually a finite series. That's funny. So we pretend we don't understand anything, we just plug the things normally. So we have summation from 0 to 4, because the fifth derivative is 0, sixth also, so basically this series is actually a finite polynomial. We plug all the pieces together and miracle, miracle, we get the same expression. So the Maclaurin series for our polynomial is actually equal to the polynomial. So obviously this is a finite polynomial, so it's this series is converging for all values of x, so there's nothing special there. That was funny. Well, let's complicate things a little bit. So we have the same polynomial degree 4, but this time we want to find the Taylor series centered at 2, just for fun. So we now evaluate function at 2 and all the derivatives at 2. So the derivatives are the same. We evaluate them at x equals 2. So x equals 2, we plug the numbers. The last one is 48, it's a constant. So for all values of x, it's 48. And after that, as we saw, all the derivatives, fifth derivative, sixth, and etc. are 0. So again, we will have a polynomial degree 4, obviously. But this time it's centered at 2. So we have x minus 2 to power n, and all the derivatives are evaluated at 2. So we now plug the pieces together, do some algebra, and we get a polynomial of degree 4. Obviously it's equal to this, but just rewritten differently, and it's centered at x equal 2. So this is interesting. We already knew that a given function has many Taylor series depending on the center of the series. So if the series is centered at 0, we have one expression for the Taylor series. If the series is centered at 2, we will have a different expression. So for each different value for the center, if it's 7, we will have a different expression. So we knew already that for a given function, the center of the series will change the shape of the final answer, let's say. And we see it here also for the polynomial degree 4. So this is a little bit funny. It's just good to realize that Maclaurin series is equal to the polynomial, but Taylor series centered elsewhere, not at 0, but in some other value, will have a different shape. So that's funny to see. If we need, in general, to find a Taylor series for a function that we already know, but the argument is different, so here sine 3x. So what do we do? Well, in general, you will take your Taylor expansion for sine and just replace x by 3x simply. And we know in this case, since this is good for all x, it remains good for all x. So this is a simple procedure, there's nothing special here. Another example, we have to find a Maclaurin series for x cosine 5x. So we know the Taylor series for cosine x. We will replace x by 5x as a first step, and then multiply everything by x. So it's just a simple expression. So the power here on x is 2n, and we multiply by x, it's going to be 2n plus 1, the power of x, right? So nothing special, it's just straightforward plug-in. Another example with another plug-in, cosine, and then we change x for x squared, so nothing special there. Now this one is a little bit funny, because the function is 2 to power x. So we need the Maclaurin series, so Taylor series centered at 0 for the function 2x. So we are using 2x to generate the Taylor series at 0. So we need all the derivatives. So we need to remember the derivative of 2x is 2x ln 2, and then the second derivative, obviously ln 2 is a constant. So we again differentiate 2x, which is 2x ln 2, so times ln 2, that's why we have square. So you see all the successive derivatives, the only difference is that the power or ln 2 keeps increasing in lockstep with the derivative. So that's important to have the general term for the derivative, the shape of the derivative. Now we evaluate it at 0 because we are asked for the Taylor series at 0, so Maclaurin series. So we put x equals 0, so 2 to power 0 is 1. So it's simple expression for the derivatives, evaluated 0. Now we all bring everything together to the formula for the Maclaurin series, and we get the general term for our Maclaurin series. To find the radius of convergence, we need to use the ratio test as usual. So we use this expression here in the ratio test, shake things a little bit, and we see that the limit here 1 over n is 0, so regardless of the value of x, this is always 0. So by ratio test, our series here is convergent for all values of x. So radius of convergence is infinite. So that was a cute expression. Well, let's complicate things. We have here log x, but instead of our usual expansion around 1 for log x, we centered it at 2. So now we need to evaluate function and all the derivatives at 2. Okay, so need to differentiate log x, so 1 over x, and then derivative of 1 over x, negative 1 over x squared. And again, it is important to keep the factorials for the general shape of the derivative. And then we spot the change of sign. So all the even derivatives have negative sign and all the odd ones have the positive sign. So we need to be careful to spot that. And then you see fourth derivative, x to power 4, but factorial 3. So 4 minus 1, right? So that's the shape, the general form of the derivative here. And now we evaluate all the derivatives at 2, so we get an expression there. So just plug x equal 2, nothing special. So this is the general form of the derivative that we will use in the formula for the Taylor series. And again, it is centered at 2, so we have x minus 2, right? And the derivative is evaluated at 2. So we just plug the pieces together. So the derivative of order 0 is the function. So the function at 2 is ln 2, right? And then you see the summation starts at 1 for all the derivatives. So it's a little bit different from what we are used to, because the first term kind of doesn't respect the pattern, because we have a constant plus and then we have a pattern with the derivatives. Okay, fine, no trouble. It's not going to change much in our life. So once we simplify things a little bit, we get the general expression for the Taylor series, centered at 2. And the general term is this expression here. So we need to find the radius of convergence using the ratio test as we usually do. So we plug everything together. We have x minus 2 over 2 that will go out in the absolute value. So here the limit is 1. Careful. So now for the convergence to happen using the ratio test, this expression needs to be smaller than 1. So it means that x minus 2 needs to be smaller than 2. So the radius of convergence is 2. If we want to get the interval, we just keep working and we get interval is from 0 to 4. So that's a little bit of algebra there. So basically we are able to find the expression for the ln x centered at 2, right? Previously we found it centered at 1, so procedure is similar. Now this example is very interesting and it's important to pay attention. So we want Maclaurin series, so Taylor series centered at 0 for the function sine square x. So it's important to use the identity with half angle formula. Very important, otherwise you will need to multiply series for sine x with itself, so that might be more complicated. An easier path is to use the half angle formula for sine square. So 1 over 2 factor of 1 minus cosine 2x. And now we proceed. So once you have this formula, the rest is just plug and play, because we have the series for cosine, and we will replace x by 2x, obviously, and then we have 1 minus, so we simplify things a little bit, and then we will multiply everything by 1 over 2. So what happened here with 1 minus cosine 2x? So the cosine 2x starts at 0, so this is 1, so this will be 2 to power 0, which is 1, x to power 0, which is 1, 2 times 0 is 0, 0 factorial is 1, so the first term is 1 actually. So for n equals 0, the first term will be 1. So we have 1 minus 1, so that goes, minus the rest of the series. So that's why you have minus, and then the rest of the series started from 1. So now you can leave it as is, or you can say, okay, well, the negative sign here, I can bring it inside. So you can do that if you wish, or leave it as is, it's fine. So 1 over 2, we just multiply everything with 1 over 2. So you can leave it here, or you can say this is negative 1 times 1 over 2 times the rest of the series. So basically the signs are changing, so you have n plus 1 as the power of negative 1 here. Also you could say, okay, I'll bring 2 in here, so the powers of 2 will change. It's not 2n, it's going to be 2n minus 1, because I'm dividing by 2. So it's up to you, do you make it more compact, or you leave it as is here, a simplified form. Obviously, if you need to find the radius of convergence, what do? Well, you could use the ratio test as previously, or you could just say, hey, the cosine is valid for all values of x, and I replaced x by 2x, so it's still valid for all values of x. Here I just eliminated one term, so it's still valid for all values of x. So basically you don't need to redo the ratio test. Another example of use of the Taylor series for the computation of integrals. So here we have x squared sine x squared. So normally this would be a little bit difficult for us to integrate, to find the antiderivative. So what do? Well, we proceed as usual. We know the series for sine x, and then we replace x by x squared. So we get the expressions simply by replacing x by x squared. We multiply everything by x squared again. So the powers for x change. You see here we had 4n plus 2. Now if we multiply the entire series by x squared, it's going to be 4n plus 4. So 4n plus 2 plus 2. So that's why we have plus 4. So we have the series immediately for the complicated expression, and now we need to integrate. Well, lucky for us, we know that the power series, we can integrate term by term. So basically the integral of the series is equal to the integration term by term, and we integrate only the part with x. So integral of this is 4n, so plus 4. It will be plus 4 plus 1, so that's why we have 4n plus 5 divided by 4n plus 5, obviously. And whenever you integrate, don't forget the constant. Now we remember that whenever we integrate or differentiate a series, the radius of convergence remains the same. So here the radius was infinite, so this is valid for all x. It remains valid for all x. So basically, even if it's very difficult to find the antiderivative for this function here, well, we can have a Taylor series expansion for the integral. So that's funny. Another example where we integrate complicated expressions. So here is cosine x minus 1 divided by x. So if we need to integrate this, it's going to be challenging, but we can use infinite series to see what happens. So again, cosine, we remember the expression, we subtract 1 and then we divide by x. So if I divide by x, the power of x here will be 2n minus 1, as you see here. So it's kind of very quick to find the Taylor series, or in this case Maclaurin series, for the complicated expression of the integrand. And now I need to integrate everything, so I integrate this side and the series, and this is a power series, so we integrate term by term. We are used to this now. So we integrate the term with x only, so the integral here will be 2n minus 1 plus 1, so 2n divided by 2n. So we combine everything. It's important to keep the brackets. You see from the series we have 2n factorial, so it's important to keep the brackets proper. And as we said, the radius of convergence remains the same. Another example with tan inverse of x squared. So tan inverse is one of those series that we need to remember. Or if you don't remember, you could actually integrate 1 over 1 plus x squared, that series, and get the tan inverse. And that series also comes from the geometric series that we used in 11.9. So we, let's say, remember the expansion of tan inverse, and it's valid for x in absolute value smaller than 1. So we replace x by x squared, so straightforward replacement, nothing special, right? X squared needs to be smaller than 1, so x is still smaller than 1. And now we integrate the expression term by term, obviously. So the integral of this, don't forget the constant, so the power here increases by 1, so we just make sure that we don't forget pieces. And the radius of convergence remains the same for integrals and the derivatives. So here the radius of convergence was 1, so it remains the same. So these are like straightforward applications, nothing special. What happens if I need to find a definite integral? So I have the two bounds of a special function. So we need to evaluate this definite integral using the series, and they want 4 decimal places to be correct. Okay, let's see how it works. The first part of the procedure is always the same. You have one of those functions that you know, the Taylor series, and then you multiply here by x cubed. So basically the power here, it will be 2n plus 1 plus 3, so that's why we have 2n plus 4. We have our interval of convergence here, so the radius is 1 again. And now we need to integrate, so we integrate piece by piece. Don't forget the constant, so I'm just integrating this thing fast, so it's going to be 2n plus 5 divided by 2n plus 5, so right, and the rest I copy. And now I need to evaluate this series at bounds 0 and 1 over 2. You see my interval of convergence is negative 1, 1, so both bounds are inside the interval of convergence of the series. Very important, because if they give me to integrate between minus 75 and 62, well, this expansion is not going to work. So I need to have my bounds within the interval of convergence, and here interval of convergence is from negative 1 to 1. So 0 and 0.5, they belong to that interval. Now, as from the expression here, I see that when I evaluated x0, all of this will be 0. So one part of the series will disappear anyways. So I only need to keep the part with x equal 1 over 2. So the series for the definite integral that is given is actually this one. Okay, great. So now we need to find an approximation for this expression. So for the value of the integral using the expression of the series. And we realize that this is an alternating series. So we are lucky again because we remembered for the alternating series, the error is smaller than the next neglected term, right? The absolute value. So they want 4 decimal places. All right, let's expand a little bit this series to see how these terms look like. So it's an alternating series. So these are our terms, and they want us to have the precision of 4 decimal places. Okay, so again I need to, by trial and error, figure out which of these terms I will use as the error. So I will take these 2 candidates to see how they compare to the correct expression. They want 4 decimal places, so that's 10 to the power minus 5. So let's see what happens if I evaluate this term. The value is 4.3, 10 to the power minus 5, so that's not good enough. I need 1 times. And then if I take the next term, it is 6.8 to the power minus 6, 10 to the power minus 6, that's good. So this term will be my error, so it will assure that the approximation of this integral, when I use only these 3 terms, will be correct to 4 decimal places. So I'll just use these 3 terms. The 4th one doesn't change the 4th decimal because it is 10 to the power minus 6, right? This term here. So I will use the first 3 pieces to approximate the value of the integral. So now you just add them using your calculator. So this approximation is correct to 4 decimal places because the error is smaller than the next neglected term. So this was a little bit of trial and error. So I had to use the expansion and then test 1 or 2 of these expressions to see which one satisfies the condition for the error. And then that will be my error estimate. The rest of the series in front will be actually my approximation. Okay, so that's how we proceed normally. Another example with sine x to the power 4, integral between 0 and 1. Again, they want 4 decimal places. So I remember the series for sine x, and then I replace x by x to the power 4. I get the series, I integrate this series, term by term obviously. So here we had 8n plus 4. Integral will be with 8n plus 5 divided by 8n plus 5. Great, constant. Then I evaluate between 0 and 1. So I evaluate the series between 0 and 1. And again, when n is 0, this is x to the power 5. Then when n is 1, this is x to the power 13. So when I evaluate it at 0, everybody will be 0 anyways. So I will have only the part with x equal 1 that will survive. Okay, so this is my series result, series that represents the value of the integral between between 0 and 1. So again, this is an alternating series magically, and we know the error estimate is the next term neglected. So I will again expand a little bit this expression to figure out how many terms I need to keep to add to get an approximation, and which term will be the estimate of the error. Again, it's by trial and error. I try 2 of these. So I try the 3rd term and 4th just to see. So the 3rd term doesn't satisfy the condition because I need 1 times 10 to the power minus 5, but this is like 4 times 10 to minus 4. That's not good enough. And the next guy is satisfying the condition. So basically I will use this guy as a error estimate, and the 3 guys before, this will be my approximation. So I add them together and I get my approximation. Again, this is an alternating series. That's why we use the result related to alternating series that says your estimate of the error is the next neglected term. So if I use the first 3 terms, the next neglected is the term number 4, and that term is actually estimate for the error, and it's equal to 6.8 10 to the power minus 6, which is smaller than what is required as error in the question. So that's why I use this guy as the estimate for the error, and the first three guys are used to approximate the integral. So that's how we get the value, approximate value for the integral. So here another example. Again, we have a function for which we don't know the antiderivative. It's going to be complicated to compute, and we need to find an approximation that is good, where error is smaller than 0.001 and the integral is between 0 and 0.5. Again, the procedure is the same. We have expansion for exponential, change x for minus x squared. We get a different Taylor series, and then we multiply it by x squared, so the powers of x here will change. So we have 2n plus 2. So now we are good to integrate this with respect to x. Don't forget the constant. So integral is here. Now we need just to evaluate it at the bounds 0 and 0.5. And again, if I check the expansion, you can expand a couple of terms just to see that actually you have x to power 3 plus some other terms. So basically everything that is evaluated at x equals 0 will be 0. So that's why at the end you will just have 0.5 to power 2n plus 3. So that's what you have, 1 over 2. So again, this is by magic alternating series. This is very useful to estimate the error, which is the next neglected term. I expand a little bit, and as usual by trial and error, I try to find which term here satisfies the condition. The error needs to be smaller than 0.001. So I try a couple of terms. So I tried this guy, well, it didn't satisfy. It's almost there, but not really. Then the next term satisfies the condition. Fine. So basically I can use this term as approximation for the estimate for the error, which means the first two terms will be used as approximation for the integral, because all they want is approximation good for 0.001. Okay, so the first two pieces are the approximation, and the third satisfies the error estimate. So this one is even easier to compute because they didn't require much from us as error. Finally, we can also evaluate the limits using the Taylor series, and obviously again it needs to be set up in a proper way so that things cancel out properly, otherwise it defeats the purpose. So here we need to compute limit of x minus ln 1 plus x, everything divided by x squared, when x goes to 0. Again, I know we could use L'Hopital a couple of times, fine, but the idea is to see how we can use the Taylor series to evaluate the limits. So basically we need to remember the expansion for ln 1 plus x, and then so x minus all that series divided by x squared. So things simplify a little bit. X minus x is 0, and then everybody else changes the sign. Then we divide by x squared. Obviously everything is set up in a way that it looks nice at the end. So the powers of x change, so these simplify, and then here it will be power x, then power x2, x3, etc. So now we evaluate at x limit when x goes to 0. So all these pieces here are 0. The only surviving is 1 over 2. Okay, it looks too simple, but that's the idea. The idea is to use the series to evaluate these integrals, these limits, but we have some special expressions that are cute. Another one with the sign, and as you expect, they give us sign minus some expression, which is actually a couple of first terms in the expansion. So everything is set up in a way that things look cute. So again, these simplify, first two pieces go, and then just by miracle we are left with the powers 5, 7, etc., and we divide by x5. Wow. So things simplify here, and then again when we take the limit, all the terms with x go to 0, and we have one survivor here, 1 over 5 factorial. Okay, yeah, no, it looks a little bit naive, but it's fine. The last one, so we have an expression and then we have tan inverse, so we need to remember the Taylor series for tan inverse. So we have the first part times 3 times the Taylor series for tan inverse. And by miracle, obviously, things simplify in such a way that we can easily find the limit. So those are some practice problems. It's important for you to try to do the process by yourself, to write it just to be comfortable with the process. I know it's not too complicated, but still it's important to make sure that you are comfortable with the process. So that's it. I hope you will solve some problems, and on the slides obviously these are problems from the book, the suggested problems, and even more. So basically you can practice having all the solutions also.